Hi, my name is Vera, and today I will present our paper titled Trace Oddity, Methodologies for Data-Driven Traffic Analysis on Tor. This is joint work with my colleagues from KU Leuven and our collaborators from Bochum and Radboud universities. Traffic analysis attacks against secure and private communications seem like a never-ending problem. In case of Tor, while it protects the source and the destination of private communication, the traffic metadata remains available for passive analysis. Attackers can still attempt to de-anonymize Tor users and their activities on the web. The attacks vary in their goals and capabilities, and the end-to-end confirmation attack that I will talk about today involves a very powerful attacker, for instance a nation-state adversary, who has access to both ends of communication. Namely, the attacker observes traffic between the Tor client and the entry node of the network, and between the exit node and the destination. These two segments can be correlated to de-anonymize private users. While there are many intriguing aspects to this attack, in our study we looked specifically at the experimental setups that are used in research labs for approximating attack performance in the wild. The fundamental issue there is that while generating our own client-side traffic is feasible, collecting traffic on the other side is really challenging. As researchers, we cannot trivially obtain access to the exit nodes in a safe way, as that would come with ethical implications because we would expose real Tor users. It is also infeasible to monitor traffic on the destination itself, as we would need access to a lot of web servers to provide proper diversity of the hosted content. So the state-of-the-art solution is adding a proxy jump. When traffic needs to pass between the exit node and the web server, we enforce a detour. Instead of going directly, the traffic first passes through a proxy server where it can be captured. So we don't need any exits or destinations anymore, and we do not need to see any real traffic, but only our own generated traffic that passes through our own controlled proxy. And this is currently how science approximates end-to-end confirmation in the real world. What we did in our studies, we started analyzing this setup and wondering whether this artificial proxy jump brings any issues for attack simulation. Previously, the impact of the proxy was seen as negligible or even claimed as disadvantages for traffic analysis, meaning that scientific results probably underestimate severity of end-to-end confirmation attacks. However, our intuition was that using a proxy can play in favor of the simulated attacker. So let's take a look at this map. Consider a Tor client, a web server, and 3 Tor relays located in Europe. The attacker would monitor the traffic on the exit node and at the entry side, where we can also capture it. Then we would need a proxy to collect the exit traffic segment. However, when that proxy is placed arbitrarily, for instance, like here, somewhere in the US, what happens is that we introduce an intercontinental hop that would otherwise not be there. This inevitably causes some timing overhead. Now, this of course depends on the specific locations. That doesn't always happen. However, given the diversity of the locations and Tor circuits, if you only have a fixed proxy for the entire dataset, such additional hops will happen occasionally, if not regularly. This possibility that the setup occasionally introduces certain artifacts in the data can be problematic. Specifically, we thought that introducing such artificial diversity in traces may make them more distinguishable for the simulated attacker, which would lead to overestimation of attack performance on such data. So then we hypothesize that the single proxy overhead influences the attack evaluation in favor of the attacker. And to test this out, we decided to reduce this timing overhead by adding multiple proxies to the setup and seeing what happens. So for this new multi-proxy setup, we distribute 18 proxies around the world. Here you just see a close-up. And we chose 6 primary locations following the actual distribution of Tor relays, especially exits. And then for every Tor connection, we first predict the next circuit that will be picked by Tor. Then we select the proxy that is closest to the predicted exit, following the idea of reducing the overhead of the detour, and then we can do our measurements. So this is the main idea behind our multi-proxy setup. First, we perform a preliminary analysis in terms of timing overhead to see if a multi-proxy setup changes anything. So we want to measure timings in the original single proxy and the proposed multi-proxy setups in comparison to the no proxy setup that the real-world attacker would use. While we cannot collect actual traffic without a proxy, we can still measure round-trip timings. So the results are as follows. You see on the plot the blue-colored single-proxy timings, they deviate from the no-proxy timings in green, while the multi-proxy timings appear to be like a really good approximation of no-proxy timings. So we see this factual difference, but we still don't know how relevant these deviations in timings are for the attack. What if it doesn't matter how closely our setup approximates no-proxy timings? To answer this question, I will first briefly introduce the state-of-the-art end-to-end confirmation attack, which at the moment of our study was DeepCore. DeepCore uses a deep neural network to correlate traffic flows, and each pairs of flows are represented as their inter-packet delays, that is timings, and packet sizes. As you can see, half of this signal is timing, so it definitely plays some role, but we still need to evaluate if the attack benefits from the timing overhead that we suspect the single proxy introduces. To find that out, we collect actual traffic through both setups. We try to fix as many variables as possible, such that it's only the proxy setup that differs between the two datasets. So we end up with roughly 8,000 traces for single proxy and multi-proxy datasets. So now, to know whether a single proxy at a fixed location leads to an overestimation of attack's performance, we need to run DeepCore, which is a two-dimensional convolutional neural network, on these two datasets and then compare performance. But how exactly would that comparison look like? It might seem straightforward at first. We run the attack in both datasets, and if the single proxy attack performs better, then our hypothesis is confirmed. However, we all know it is not trivial to compare data-driven attacks. In reality, it is more complicated. In our paper, we recognize many challenges in reliable comparison of data-driven attacks. First, one, of course, needs to establish an equal ground for comparison. This can mean infinitely many things. For instance, this relates to hyperparameter tuning. How do we make sure both attacks are tuned using similar approach and effort in terms of hardware, time, and other resources? Are we using the same algorithm? And also, how sure are we that the difference in attack performance is due to the underlying learning algorithm or architecture and not due to the different learning capacity of two models? The next crucial aspect is, what do we even mean when we say attack performance? Which metric do we use to say that attack is successful? Sometimes, and that is the case for end-to-end confirmation, the metric used for optimizing the attack model is not the same as the one used for evaluating and comparing the attack. So in reality, there is this tension between the algorithmic optimization goal and the final evaluation metric. The next challenge is quite general for machine learning and deep learning. We need to eliminate as many sources of bias as possible. For instance, non-determinism of deep neural networks, which rely a lot on randomness and can even be unstable. There is also risk of sampling bias, which is often mitigated with cross-validation. But what follows from this instability and potential bias is that attack performance is not just a number, it is in fact a distribution. So when we compare data-driven attacks, we compare rather limited samples of two distributions, and we really need to show statistical significance of that comparison, meaning how confident we are that among these two distributions from which we sampled performance values, one is truly better than the other. Finally, it would also be great to provide some semantical evidence as to why one attack performs better on the specific data. For that, we look into explainability of attack models. So these are the challenges that I listed, and now one could say that it's infeasible to satisfy all these requirements, which is probably true. However, if we strive to that, we will improve reliability of the results. And our research is only as reliable as the conclusions that we draw from the limited empirical evidence, so it's worth the effort. With all that in mind, we proposed a general high-level algorithm for scientific replication and comparison of data-driven attacks. And we used this algorithm in our evaluation of the DeepCore attack on the single and multi-proxy datasets. In this main evaluation, we apply DeepCore to each dataset, and that includes extensive tuning, training, and testing of deep neural networks, and then comparing the results. What is interesting is that the answer to our research question lies in every step of the attack. If the single proxy setup indeed makes the attack easier, we should be able to notice that at every step. So let's nuance our original research question. Instead of asking if the attack on one dataset is more successful than on the other, we want to find out whether the single proxy data presents a simpler learning problem than the multi-proxy data. So let's now move on to the evaluation results. You can see on these plots the automated hyperparameter tuning procedure that we performed with 120 runs per dataset. Already at this stage, you can notice that there are many more successful configurations on the single-proxy dataset than on the multi-proxy one. In other words, it appears easier to tune a model collected on the single-proxy traffic than on the multi-proxy traffic, so that's already our first clue. Next, we'll look at the training process itself. Here we have the best models evaluated on 5 parts of each dataset, and we see that the neural network trained on the single-proxy data, colored in green, converges better. So here again, the single-proxy dataset shows to be easier to train the model with. And now I'll show final results. First, the average precision of the attack on multi-proxy data is on average 11% worse than on single-proxy. Moreover, the false positives are doubled, which means that for each wrongly correlated pair of traces of the single-proxy dataset, we get 2 of those for multi-proxy, which is quite detrimental. These results over 40 runs come with a rather high statistical significance, so we can conclude that end-to-end correlation is significantly more challenging on multi-proxy data, strongly indicating that the subtle bias in timing characteristics in the single-proxy setup may well be causing the overestimation of the attack performance. While these results confirm our hypothesis, we still wanted to get some more evidence by applying explainability analysis on deep core. Our preliminary analysis of activation values in the first layer of the network showed that timings, and specifically uplink timings somehow, are consistently more impactful for the attack on the single proxy setup. This gives some additional support to our findings. A couple of extra insights important going forward is that first, even with 80% true positives, which sounds high, attack precision is in fact on average only 8%. Also, when we triple the amount of traces we use for learning, it becomes much harder to execute the attack. This is because for n traces, the attacker needs to correlate n times n pairs, so the base rate of truly correlated pairs becomes really small. The high-level takeaway is that it seems that we are still quite far from realistic estimations of end-to-end confirmation in terms of how feasible it is to exploit this kind of leakage. To facilitate future research on this, we publish our data. The traces we used for the evaluation and the code are on GitHub, but we also collected a really large dataset using our novel multi-proxy setup. This dataset is applicable for both end-to-end confirmation and website fingerprinting research. To sum up, we propose an improved data collection setup for end-to-end confirmation attacks against Tor, together with the refined evaluation and comparison practices and preliminary explainability analysis. Thank you very much for your attention.